Hey everyone, and welcome to this explainer. So today we're actually going to uncover the hidden physics of a seemingly mundane object that is quite literally holding your world together right now, the screw. I mean, just look around you. The chair you're sitting on, the screen you're looking at, the vehicle parked outside, they all completely rely on this tiny mechanical marvel. But how often do you actually stop to think about the invisible battle of forces happening inside every single threaded hole? Well, today we are going to decode that exact battle. Okay, let's just dive right in. Here's our roadmap for today. First, the secret of screws, then fasteners versus drives. After that, the forces of tightening, followed by loosening and self-locking, and finally, the V-thread variation. All right, kicking things off with section 1, the secret of screws, unwrapping the geometry. Now, I kind of want to challenge your basic perception of what a screw actually is. When you picture one, you're probably just seeing a piece of metal with spirals cut into it, right? But to an engineer, well, as our source material defines it, quote, a helical screw converts rotational motion to an axial displacement. I really want you to let that sink in for a second. You spin something in a circle, that's rotational motion, and the screw translates all that energy into moving forward or backward in a perfectly straight line, which is axial displacement. It's absolutely wild when you think about it. It's this core engineering miracle allowing human hands to exert massive linear forces just by twisting a screwdriver. And this brilliantly illustrates the concept. If you take a simple inclined plane, like a ramp, represented by the red triangle here, and you just wrap it around a cylinder, boom, you get a screw thread. This is a total aha moment. A screw isn't just a spiral. It is literally a ramp wrapped around a pole. So when you turn a screw, you are essentially pushing a heavy load up a very long continuous hill. Moving right along to section 2, fasteners versus drives. From concept to the real world. Out in the real world, engineers use this whole wrapped inclined plane concept for two very distinct purposes. On one hand, we've got fasteners, and on the other, drives. Fasteners are all about stationary holding power, joining two members together by providing a highly specified contact stress right at their interface. Think of your standard bolts and nuts. Screw drives, on the other hand, well, they use that exact same wrapped ramp for active movement. They traverse components axially. Imagine the lead screw moving a cutting tool linearly along a lathe machine, or a worm drive used for gear reduction. To put the massive stakes of fasteners into perspective, just take a look at these two real-world applications from our sources. On the left, we've got a motorbike engine cylinder head, and on the right, a massive industrial pressure vessel. Now think about this. The explosive forces going off inside that internal combustion engine and the terrifying pounds per square inch inside that pressure vessel, they are all being held back by nothing more than tiny, wrapped ramps. Honestly, those screw threads are literally the only things stopping an explosion. So how in the world do they hold so tightly? Well, when you apply torque, which is just a twisting force, to the nut, it travels right down the thread. As it hits the surface, all that torque translates into immense contact stress. The threads of the bolt are pulling up, the nut is pushing down, and those two members are clamped together with just incredible force. Which brings us to section 3, the forces of tightening, overcoming the load. Now, you might be wondering, what is the invisible mathematical struggle actually happening when we twist a wrench to create that clamping force? It all boils down to this fundamental question. How much torque do you actually need to tighten that bolt against the load? Let's go ahead and bridge the gap between the macro industrial scale we just looked at and the micro mathematical formulas that engineers use every day to calculate these forces. All right, let's look at case I here, the torque required to rotate the screw against the load to tighten it. The formula is T equals W times the tangent of phi plus alpha multiplied by dm over 2. Now, don't let the math scare you away. Think back to our wrapped ramp. W is simply the heavy load you're trying to push. Alpha is the angle of our thread, how steep the ramp is. And phi, that's the friction angle. So the crucial point is, when you tighten a screw, you're actually fighting both the steepness of the ramp and the friction of the surface. You are literally pushing the load up the hill. And that leads right into section 4, loosening and self-locking, the ultimate payoff. Okay, so we've pushed the load up the hill. We've tightened the bolts on that giant pressure vessel, but what happens when we take our wrench away and just stop applying force? Why doesn't the load just push the screw right back down the ramp? Well, let's look at case 2, loosening the screw. Notice how the formula has subtly changed here. Now it's T prime equals W times the tangent of phi minus alpha.
Because we're loosening it, we are moving the screw in the exact same direction as the axial load. We're going down the ramp. So the load, W, is actually helping us. The thread angle, alpha, is helping us. The only thing fighting us now is phi, the friction.
And guys, this brings us to the absolute climax of this explainer, the self-locking condition. The formula demands that the friction angle, phi, must be greater than or equal to the thread angle, alpha. If the friction is greater than the steepness of the thread, the screw locks itself in place. This simple, completely elegant geometric rule is the singular reason our cars, our buildings, and our machines don't just spontaneously unscrew themselves and fall apart. Friction is absolutely the hero here. On the flip side of that, we have what's known as the overhauling of screws. If phi is less than alpha, meaning the thread ramp is way too steep and the friction is too low, the screw is non-self-locking. It will literally unwind itself under the sheer weight of the load. I mean, unless you're intentionally designing a very specific kind of push drill or an automated jack, a non-self-locking fastener is basically a mechanical engineer's absolute worst nightmare.
All right, final section, section 5, the V-thread variation, adding complexity.
So far, we've been talking about a perfectly flat square ramp, but real-world screws, like the ones you just grab at the hardware store, often have different shapes that alter these base physics slightly to give us a bit of an advantage. Let's examine the V-threaded screw. Now, what's really interesting about this slide is that instead of a flat step, the thread cuts in at a sharp V shape, characterized by the included angle 2 beta. Because the surface is angled, the vertical load W doesn't sit flat anymore. It actually wedges itself right into that V shape. And this completely changes the normal reaction force, which is represented here by Rn. Because of that wedging effect, the normal reaction required to support the load actually increases. And the math totally proves it. Rn equals W divided by the cosine of beta. Since the cosine of an angle is less than 1, dividing the load by it yields a much higher normal force. And remember, more normal force equals more friction. By simply angling the thread into a V, engineers artificially boost the friction, making V-threads incredible fasteners that are even harder to accidentally loosen. So we've seen how a simple wrapped inclined plane tames massive forces, how geometry dictates locking, and how a basic V-shape can totally amplify holding power. The next time you grab a screwdriver to tighten a bolt, I really want you to ask yourself, in your everyday life, is friction just an annoyance slowing you down, or is it, quite literally, the only thing holding your entire world together? Thanks so much for joining me on this explainer, and keep exploring the incredible hidden engineering all around you.